Our world today is confronted by a warming planet, in part caused by fossil fuels energy production. We propose a potential carbon-free energy solution to this problem, the Molten Lead Fast Reactor. My name is Colin Dunn, and my group members are Luke Black, Lucian Owain, Osman Njai, and Jeffrey Wayne. Lead-cooled fast reactors are an advanced type of nuclear reactor that use lead coolant to achieve better economics, safety, and operability compared to today's light water commercial reactors. The higher operating temperature of lead leads to higher thermal efficiencies and thus better economics. Its high boiling point and non-pressurized conditions means the core will be safer and simpler. We based our design on several published LFR designs, including the Alfred, ELFR, Breast, and S-START prototype reactors.
Our main objectives for our project is designing a lead-cooled fast reactor that has 1,000 megawatts of power, which is also economically feasible, safe for a power plant, has a competitive efficiency. To the right, it's going to show a chart of our success measures that we use to gauge meeting our objectives.
To begin the first iteration of our design, we performed a literature search focusing on the Alfred and European lead-cooled fast reactors. We also examined the Westinghouse reactor for the steel alloy they used in their fuel cladding. We developed a pin cell model to act as a proof of concept, then expanded to a full fuel rod to act as the basis for our thermohydraulic calculations. We established a fuel assembly model and expanded into a full core model. To reach our second iteration, we tested several configurations of fuel assemblies before deciding that it is simply not worth it to focus on breeding in our reactor, as the breeding of fuel does not exceed the burning of fuel.
We want our core to be as fuel efficient as possible, and the way to determine that is by measuring fuel burnup. Burnup can be increased by increasing plutonium breeding and refueling the core in several different batches. After conducting advanced Monte Carlo simulations and using the non-linear reactivity model, we developed a 4-batch refueling scheme that more than doubles the burnup required by our original design objectives.
Our secondary loop consisted of a 13-point Rankine cycle with pump and turbine efficiencies fixed at 90%. Initial temperature values for the steam generator were obtained from the parameters of our lead coolant reactor design. Pressure for each stage of the secondary loop was sourced from similar LFRs. The resultant thermodynamic efficiency calculated was 44.01%. This falls short of the ideal Carnot efficiency of 58.76%, but a significant improvement on commercial PDOs, which operate at 35%. We evaluated our design parameters in several plausible scenarios, but ultimately determined that natural circulation for our reactor was not possible. Primarily, our reactor temperatures were just too low, and lead itself does not vary in density with temperature significantly enough to generate natural flow.
We developed a shielding model made of concrete, lead, and carbon steel to protect radiation workers and the environment. Our goal was to reduce the radiation dose to below the mandated annual limit of 5 rem per year. Using a 2.4 meter thick bioshield, we were able to reduce radiation workers' dose to below this limit with 270 working hours near the core. Additionally, our 60 centimeter thick containment dome reduced radiation fluxes to the environment to less than 1/10 of typical background radiation levels. Although not considered in this design, additional improvements to our core design, including placing the core underground, could result in even lower radiation levels.
Our safety assessment proves our design is safe because of a negative fuel temperature coefficient, a significant material temperature failure margins, and our control rod systems would be able to control the reactivity of the core. Nuclear reactors are known to have a large capital cost, and one important metric used to gauge the feasibility of a design is the cost of electricity. Our economic assessment shows that we have a lower cost of electricity than other advanced Generation 3 reactors.
In conclusion, our project met or exceeded all design objectives. We designed a 1,000 megawatt lead-cooled fast reactor that is compact, fuel and energy efficient, economically competitive, and adequately safe and shielded. Future work could include improving reactivity feedback and placing the core underground. Thank you for watching, and please view our poster to learn more about our project.